Okay, thank you very much, Andreas, for the introduction and for reading out the long title. Who has a title like that does not need an abstract, I guess. And thank you also to the organizers for inviting me. It's a great pleasure to be here, and I learned a lot of things. And it's a great pleasure also to present this work that was indeed performed at the Vienna University of Technology. But since the beginning of this year, I now have a new affiliation and are actually professor at Humboldt University in Berlin. And with this change, there are also new positions that are opening. So if you like what you see, maybe you just contact me and we talk. So maybe I start, while there was a very nice introduction on non-reciprocal devices, with some further introduction onto the realization of possible optical non-reciprocal devices. And I think the prime example is a Faraday rotator, who actually turns the plane of linear polarization of a wave that travels through a magneto-optical material, like a magneto-optical crystal, or it can also be some atomic vapor, along the direction of an applied B field, and the plane of polarization then turns. And actually the sense of rotation of this polarization plane is independent of the direction of propagation, which means that if you exit here with an angle beta and you come back with that polarization, you will end up here with an angle 2 beta with respect to the incident polarization. Okay? And this angle beta is actually proportional to the strength of the applied B field. It is proportional to the length of the magneto-optical material, and the proportionality constant is this constant V here, which is called Verdet constant, and this Verdet constant is a material constant which depends on the wavelength and on the actual material that you use. Now, taking advantage of this Faraday rotation, you can then realize, for example, a one-way street for light, optical isolator, by simply placing at both ends of the magneto-optical crystal here polarization filters, such that this polarization passes. And here I tune this angle beta to be 45 degrees and let it pass through a second filter, which is placed here. And in this case, if there's a back reflection, then there will be another 45-degree rotation, meaning that I end up here being polarized at 90 degrees with respect to the incident polarization, and this will simply be blocked by the polarization filter that I place here at the entrance. Okay? So with this, as I said, we realize an optical isolator where light passes from port 1 to port 2 and exits here, but if I send the light back to port 2, it will be absorbed here in this filter. By replacing these polarization filters by polarizing beam splitters, we can also turn this optical isolator into an optical circulator, because here, if I now send the light back from in the reverse direction, rather than being absorbed, it will be reflected out of this port 3 here. And if I send light into port 3, it will come out of port 4. And if I send light into port 4, it will come out of port 1. So there's a routing scheme, port 1 to 2, 2 to 3, 3 to 4, 4 to 1, and that is actually the routing scheme of a 4-port circulator, which is a very important component, as Andreas nicely explained, for many applications. Okay. Now, if you consider that the field strength here, okay, is typically limited to, say, a Tesla, because you realize this permanent, this magnetic field with a permanent magnet, and you consider a bulk optical isolator where this crystal here is typically 1 centimeter long, then in order to fulfill this requirement of beta being 45 degrees, the Verdet constant has to be on the order of 80 radians per Tesla and meter. And such a Verdet constant is available for a range of magneto-optical materials and for a large range of wavelengths, so you can just buy off the shelf very performant optical isolators basically for all relevant wavelengths. However, they are bulk in the sense that you have a 1 centimeter long medium. If you now want to miniaturize these isolators, say reduce the length of the medium by a factor of 100, then you're still limited to the same magnetic field strength. So basically what you have to do is to increase the Verdet constant and have a Verdet constant, say, of 8,000 radians per Tesla and meter. And it turns out that there are not, for all wavelengths, materials available that give you such a high Verdet constant. And secondly, actually such a high Verdet constant also comes with a high absorption. Okay, so you, at the expense of the transmission through your isolator, you can increase the Verdet constant. However, if you care about losses, say if you would like to manipulate information at the level of single photons and control these single photons, then you see that miniaturizing and the associated higher loss is a problem. And so this already hints on the problem of also integrating non-reciprocal devices into integrated photonics being a challenge. Okay? So in integrated photonics, you basically have all kinds of devices available that you can think of. However, for the reasons that I was explaining, and for an additional reason, which is that typical integrated photonic waveguides are birefringent, and it's not possible to smoothly rotate the plane of polarization along the direction of propagation because the integrated photonic waveguide is polarization maintaining. Commercially, non-reciprocal integrated optical devices are simply not available even after several decades of research. Okay? And research-grade realizations are available, but however, most of these demonstrations, actually all of them up to our demonstration in 2015, failed to combine a high isolation with a low forward loss. Okay? And here I sketch some of these research-grade realizations of integrated optical circulators and isolators. And what you see here is like a substrate with waveguides in green on top. And then what is being done is there is a magneto-optical film placed on top of the waveguides. So it couples to the evanescent field that penetrates into the magneto-optical film. However, interestingly, the magnetic field is applied in a direction orthogonal to the direction of propagation. Remember, in the bulk optical isolator, the direction of the magnetic field was along the direction of propagation, and somehow then it seems clear that that can give rise to a rotation of the polarization because the B field is like has a handedness. However, here the B field is orthogonal to the direction of propagation, and one might wonder, how can a B field that is orthogonal to the direction of propagation tell the light you're not allowed to pass in this direction, but you're allowed to pass in the other direction? And the underlying physical effect is actually so-called spin momentum locking of light, and I think that this effect is most easily understood by simply considering water waves. Okay, so now we will have a short excursion to the physics of surface waves on water. So when you look at the amplitude of a surface wave on water, then the amplitude diminishes when you go away into the, when you go deep into the water, because the speed of sound down here in the bulk is much, much higher than the surface wave here, the speed of the surface wave. And so this decreasing amplitude in direction orthogonal to the direction of propagation in conjunction with the continuity equation. So this is the hydrodynamic equation for an incompressible liquid, which says that the divergence of the velocity field of the water has to vanish, tells you that you cannot have the gradient of amplitude in the transverse direction without actually having a component of the amplitude in the longitudinal direction. So, and in addition, this longitudinal component is forced to oscillate at phase quadrature with respect to the transverse component, meaning that the water moves in more or less circular orbits in a water wave, okay? And now this kind of motion, circular motion in a plane that contains the direction of propagation has important consequences when it comes to reversing the direction of the wave. Because if we reverse the direction of the wave here, then it's like running the movie backwards. And obviously then the water, which circulates clockwise for a left to right moving wave, will then circulate counterclockwise for a right to left moving wave. So the sense of circulation flips with the direction of propagation. And it turns out that the same thing occurs for the electric field in a surface wave, like an evanescent wave above a dielectric interface. And we will make use of this effect then to realize a chiral coupling of emitters to such wave-guided modes, okay, where chiral here is a synonym for propagation direction dependent. Okay, so we realize a propagation direction dependent coupling of emitters to guided waves in the waveguide. So rather than having the situation where, say, an atom coupled to the waveguide emits the same amount of light to the left and to the right, we can realize a situation where the emitter emits more light to the left than to the right. And we can tell the emitter, and now send your light to the right rather than to the left. And we can even have all of the light going to the right rather than to the left. And I should stress that this effect is not limited to the experimental platforms that I'm presenting here. There's a wonderful work by all these groups here on such chiral coupling, so check out their contributions. So with this, I come to the overview of the rest of the talk. I will first present the guided modes in optical nanofibers. This is our experimental platform. Optical nanofibers are cylindrical dielectric waveguides with a diameter smaller than the wavelength of the guided light. Okay? And I will then show you that by coupling spin-polarized atoms to these guided modes, we can realize an optical diode for light, and by then mediating the coupling between a single atom and the waveguide using a micro resonator, we also can realize a quantum optical circulator. So as I said, the waveguides we are using have a diameter which is smaller, so the radius here is about 250 nanometers, meaning the diameter is 500 nanometers. Wavelength we are working with is 852 nanometers. This is the resonance wavelength of cesium. So the diameter is smaller than the wavelength of the guided light, which means that the light is not only confined inside our glass fiber here, but actually about half of the optical power is guided in the form of an evanescent wave surrounding the waveguide. Okay? And now here in this evanescent field, we have the same situation as for the water wave. The speed of light is slower in the waveguide, it's larger outside of the waveguide. The amplitude decreases more or less exponentially away from the waveguide. And then if the transversal component of the E field points in this direction, I will get similar effects as for the water wave. The reason being that the E field, the electric field outside in this evanescent field here, has to fulfill Gauss' law, which is perfectly analogous to the continuity equation for hydrodynamics. So that means that if I send a linearly polarized wave into our waveguide here, then above the waveguide I will have an E field where the vector prescribes, or the tip of the vector prescribes a circular orbit, and below the waveguide the orbit is actually clockwise. Okay? And I can now also quantify this polarization by an ellipticity vector or spin, okay, where spin now is a classical electrodynamic quantity. It's the intrinsic angular momentum carried by the light field, and this spin is now orthogonal to the direction of propagation. So it points out of the board above the waveguide and into the board below the waveguide. So what you see then is that the local ellipticity and spin actually depends on the transverse position in the mode, which already tells you that this spin that I'm talking about is a local quantity, and it's not a good global quantity anymore to describe the state of the guided mode. It's actually the total angular momentum that is conserved in all this but the spin itself is a local quantity that can even change sign above and below the waveguide. More importantly, if I now reverse the direction of propagation of the light field, this transverse spin, like for the water wave, changes sign. So when the E field turns counterclockwise above the waveguide for light propagating from left to right, it will turn clockwise for light propagating from right to left. So that means that the local ellipticity or spin changes sign with the direction of propagation, and this effect too is referred to as spin momentum locking of light. Okay, so the spin is no longer independent of the linear momentum of the guided light, but the transverse component is locked to the linear momentum, and if I reverse the linear momentum, I change the sign, then the sign of the transverse spin also has to change. And this will now allow us to realize non-reciprocal devices, actually. For example, a spin-controlled optical diode. For this purpose, the only thing we need now is scatterers that we put into the evanescent field that have a different coupling strength to sigma plus polarization versus sigma minus polarization. Because in this case, when light goes from left to right and we have, say, sigma plus polarization here, the light will be scattered out of the waveguide. But if I send the light from the other side, I have sigma minus polarization, which ideally does not couple to my scatterers, and so the light just propagates through the waveguide. And it turns out that spin-polarized atoms can be made to act as such polarization-dependent scatterers. Okay? So if I take, in our case, cesium atoms and we place it into the evanescent field and now optically pump these cesium atoms into the outermost Zeeman substate of the ground state manifold with projection of spin. So it has a total spin of 4 and then a projection of +4. And I apply a magnetic field, okay, then the Zeeman effect will tune, for example, the sigma minus polarized transition out of resonance, whereas the sigma plus polarized transition will still be resonant with the light propagating in the waveguide. And in this case, the light will be scattered if it travels from left to right, but if it goes from right to left, it will just propagate through the ensemble of atoms. Interestingly, however, it is not even necessary to apply this magnetic field. Okay? So even if I now switch off the magnetic field and this level here shifts into resonance with the light field, the transition strength of this transition in cesium is about 50 times smaller than for the sigma plus polarized transition. So this transition strength is given by the Clebsch-Gordon coefficients and 3J and 6J symbols. So it's a property of the angular momentum of the cesium atom. And I can actually realize now an optical isolator which does not necessarily need an applied magnetic field. And so we did this by applying a magnetic field in this case, and saw indeed a strong asymmetry between the forward and backward transmission. So the isolation was 8 dB, while the forward transmission was still 80%. Now, depending on who you talk to, 80% transmission is, well, not impressive at all, or if you talk to other communities, they will just roll in the dust in front of you. But actually, this combination of 80% forward transmission and 8 dB isolation can be converted into a figure of merit, which would be dB of isolation per dB of forward loss. And in terms of this figure of merit, this realization was world record at the time when this work was done. Okay? Even though 8 dB doesn't sound like a hell of a lot neither, because you can buy like 30 dB or 60 dB isolators, but remember, this is an integrated optical isolator which acts on fiber-guided light fields directly. Okay? And this job was done, you can actually, we could work that out by a few 10 atoms here. Okay? And I would like to stress again that the sufficient precondition for this to work is the asymmetry in transition strength, meaning that an external magnetic field is not required, And even, you could say, well, spin-polarized atoms are little magnets, but even the atomic magnetization is not fundamentally required. You can think of level transitions in atoms where the G factor is 0, okay, but you still have this asymmetry in transition strength, so there is no magnetization associated with the spin polarization. However, with the cesium atoms here, there was magnetization associated with spin polarizing them, okay. Now, I would also like to stress that while this optical isolator is based on a quantum optical effect, it is not a quantum device in the sense that it will not be possible to operate this isolator in a quantum superposition of passing light from left to right and passing light from right to left, okay? Why? Because the whole thing is based on the interaction of an ensemble of atoms which is in this stretch state. And if I now wanted a quantum superposition of the isolator passing light from right to left and left to right, I would have to prepare all 27 atoms in a quantum superposition of all atoms being in this spin state and all atoms being in the opposite Zeeman substate. So that would be a 27 atom Greenberger, Horn, Seilinger entangled state, which in the laboratory will be not possible to prepare and would be very susceptible to decoherence. If the job was done, however, by a single atom, okay, so this isolator was realized by a single atom, then it would be straightforward to prepare the atom in a quantum superposition of these two spin states, right? However, a single atom here only has a coupling strength of a few % to the optical mode. So a single atom would make a very poor isolator, right? So somehow we now have to increase the coupling strength of a single atom to the waveguide mode in order to realize a single atom non-reciprocal device. And this can actually be realized by mediating the coupling of the atom to our waveguide by means of a so-called whispering gallery mode resonator. So this is a cylindrically symmetric dielectric structure which sustains or confines light by continuous total internal reflection at the surface here, okay? And now the nice thing about the whispering gallery mode resonator is that these modes of the whispering gallery mode resonator exhibit the same spin momentum locking as the evanescent fields of the nanofibers, because we are again coupling to an evanescent field and the electric field, the transverse component oscillates radially, so we can actually maintain these chiral coupling in the presence of the whispering gallery mode resonator. I should stress that the same system is also used by Barak Dayan at the Weizmann Institute of Science, and I should stress that these experiments were now carried out with rubidium-85 rather than cesium, which means that the ground state spin is now 3 rather than 4. However, if we now prepare the atom in this outermost Zeeman substate, we again single out this V-level scheme, and we again have a strong cycling transition here and a weak sigma minus transition, which for the case of rubidium is now a factor of 30 weaker than the sigma plus transition, okay? So if we now send light from the left into the waveguide, it will circulate counterclockwise in our whispering gallery mode resonator, and due to spin momentum locking, this gives rise to sigma plus polarized light in the evanescent field of the resonator, and this drives this strong cycling transition in rubidium-85. Now if I look at the transmission of this waveguide here as a function of detuning of this light field, then I see actually for the empty, let's first look at the gray line here. So for the empty resonator, I see the whispering gallery mode here showing up as a resonance which goes down to 0 transmission at resonance. Now this is actually possible to achieve by tuning the gap between this waveguide here and the whispering gallery mode resonator and achieving the so-called critical coupling condition where the transmission is close to 0 at resonance. And if we now look at the transmission of the same system when I introduce an atom, then on this transition we are in the strong coupling regime where the atom now hybridizes the resonator resonance and I get two new normal modes, and they are split by 2 times the vacuum-Rabi frequency, which is about 17 megahertz here. And we see that we have a high transmission where there was formerly no transmission. Okay? Now if I send the light from the other side into our coupling waveguide, however, then the light circulates clockwise in the resonator, which then, due to spin momentum locking, gives rise to sigma minus polarized light in the evanescent field. And that means that this light field drives the weak transition, and in this case it's so weak that the presence of the atom does not modify the resonator spectrum. It's almost not there, and you don't see any real difference between the spectrum with and without atom. Now this is a very non-reciprocal device, because for one and the same optical device, sending light from the left or from the right, I get 2 qualitatively different transmission spectra. And in particular, this realizes an optical isolator, because if I consider the on-resonance transmission, if I send light from the left, the atom is strongly coupled, the light cannot enter the resonator and just goes on, okay, and I have high transmission here at resonance, whereas when I send the light from the other side, the atom is weakly coupled, the light enters the resonator, is dissipated therein, and thus I have low transmission. So in this case, we realize an optical diode, and the isolation was even higher than for the ensemble-based case. So we had an isolation of 13 dB with a forward transmission of more than 70%. So here we control the propagation direction of light with a single atom. However, this device is still not a quantum device in the sense that it's still not possible to prepare, or well, you can now of course prepare the diode in a quantum superposition of passing light from left to right and right to left by preparing the atom in a superposition of spin states. However, since the device is based on losses, the first photon that I send into the diode will perform a measurement of the spin state of our atom and will collapse the superposition of spins, and the following photons will not be treated equally because I just collapse onto one or the other spin state. So in order to transform this into a true quantum device, we would have to now get rid of the losses, and this is actually possible by simply coupling a second fiber here to the resonator, such that before being dissipated inside the resonator, the light is coupled out into this drop fiber here. Okay, so now we approach a second fiber to this resonator, and in this case I still have a diode between port 1 and 2, because when I send light back from port 2, the atom is weakly coupled, enters the resonator. However, now the light before being dissipated in the resonator is outcoupled to port 3. If I send light into port 3, the light cannot enter the resonator because the atom is strongly coupled, so it goes on to port 4. If I send light into port 4, then the atom is weakly coupled, light goes into the resonator and comes out of port 1. So the routing is port 1 to 2 to 3 to 4 to 1, and this is actually the principle of operation of an optical circulator. Now the parameter that we can tune in this scheme here are the coupling strengths of these 2 coupling fibers to the whispering gallery mode resonator. And in order to characterize the performance of the circulator, we can then simply record the isolation of these 4 diodes, 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Okay? And if I measure the forward and backward transmission as a function of the coupling strength of these fibers to the resonator, then I get a lot of data points. I don't want to go through all of them, but rather just say that there is a sweet spot of coupling strength. So here I have coupling strength of the fiber to the resonator versus transmission, and for a given optimal coupling strength, I do have high forward transmission and low backward transmission, high forward, low backward, high forward, low backward for all 4 diodes. If I convert this into isolations, then the isolation is at least 5 dB and the maximum is about 10 dB. And it turns out that the photon survival probability is still higher than 70% in this scheme. Now for time reasons I cannot go into the details, but take my word for it that if we now flip the spin, this is what we did, then actually the routing also changes. So rather than going 1 to 2 to 3 to 4 to 1, when we flip the spin of the atom, the routing is 1 to 4 to 3 to 2 to 1. And actually for this experiment there was a small magnetic field applied, only to give some guiding quantization access to the atom. But when we flipped the spin, we left the magnetic field unchanged. So it's really the spin that induces the non-reciprocity. And I would also like to stress that here there is not the magnetic field, but the spin that induces the non-reciprocity. And why does the spin break Lorentz reciprocity? It's because the spin has the same time reversal properties like a magnetic field. If I reverse the time, then my, say, MF equals +4 state becomes an MF equals -4 state, because you can imagine the spin like being a small top that just flips sense of rotation when I reverse time. So that means that we have a spin-controlled routing here, and by flipping the sign of the spin, we can actually go from roundabout for light in mainland Europe to, say, the UK, okay? So with this, I summarize my talk. I introduced the strange polarization properties of guided modes and optical nanofibers and showed that the local polarization is locked to the propagation direction. And then I showed you that one can realize optical diodes and circulators based on this effect by coupling spin-polarized atoms to these guided modes. Actually, these devices can be seen as nanoscale quantum optical analogs of what people use in microwave technologies anyways for a long time, so microwave ferrite resonance isolators. However, here the Higgs lab is replaced by a bunch of atoms or even a single atom, okay? So where can all this lead to? First of all, I showed you some optical signal processing and routing in an integrated quantum optical environment. Quantum optical in the sense that the scheme is also compatible with routing single photons. It's not based on a nonlinearity like some other non-reciprocal devices where you need high optical intensities to achieve isolation. So this is a linear scheme which can also route very low light powers. I think it also shows you what I showed here highlights that we should think over again the so-called one-dimensional atom model. So this is the simplest possible model of light-matter interaction, a single two-level atom coupled to a single pair of counter-propagating field modes, because all the truths and dogmas that we know about the one-dimensional atom model are actually based on the assumption of symmetric coupling to these counter-propagating modes. And here what I showed you is that you can have full chiral coupling where the atom is only coupled to, say, the right propagating mode and doesn't even see the left propagating mode. I didn't talk about the nonlinear behavior of this quantum optical circulator, but since it's based on a single atom, it is also nonlinear at the level of single photons, and this nonlinearity can be used to realize photon sorters, quantum non-demolition measurements of light, and error-proof Bell state analyzers. And actually this chiral coupling of atoms to a single bosonic mode also gives rise to interesting new quantum many-body systems where the two-level systems are talking to each other via a waveguide. However, it's always only the left atom that is talking to the right atom, but the right atom cannot information back to the left atom. And this actually gives rise to interesting new phases of quantum many-body systems. If you would like to know more about the perspectives, you can also check out this review that we wrote with the groups of Peter Lodal and Peter Zoller that appeared in Nature. And with this, I would like to thank my co-workers who performed the experiments, and I would like to thank the funding agencies, and I thank you for your attention.